continue from where we left off in the last lecture on routing algorithms. So, let us briefly recapitulate first that what we were studying in the last class. So, recall that when we talk about routing algorithms, we essentially talk about the algorithms for computing the routing tables at each node, and the actual routing is very simple. It just does a table lookup for the destination to which the packet must be routed, finds out the neighbor to which the packet must be forwarded, and forwards the packet to that neighbor. So, we talked about different metrics for computing the routing tables, among which our current focus is on the shortest path routing. That is, we want to see how we can compute the routing tables so that packets are routed along the shortest path to the destination. To study this particular metric, we first looked at Floyd Warshall algorithm, where the algorithm starts with a empty set of vertices S, and in each iteration it adds a new vertex into S, but before it does that, it makes sure that for all u and for all v, the shortest path from u to v through the vertices in S is correctly captured in du. So, in other words, it always maintains that for all u and v, the variable duv contains the shortest distance between u and v through the vertices in S. Okay. Now, in order to maintain this invariant, in every iteration, whenever it picks a vertex w, it has to perform this updation to make sure that duv remains equal to dsuv when w gets added into S. Okay. Now, in order to achieve a distributed version of this algorithm, we realize that for a node u, all of this information is available locally except the dwv part. So, u has the value of duv, it has the value of duw, but it does not have the value of dwv. So, therefore, in the distributed algorithm, what we do is that we make all the processes synchronize at this point, they synchronize here, and the node w broadcasts its routing table, which contains the dwv for all v, that is broadcast to all the nodes, right. And therefore, each node u, when it has the dwv values, can actually compute the duv values locally and thereby maintain this invariant. Okay. So, that's what the distributed version does, that all nodes must pick the same w and they synchronize here, then dw is broadcast to all the other nodes, and then once the node u has the value of dw, it can use this Floyd Warshall check to update the value of duv. Okay. And as it updates duv, it also maintains that what is the neighbor to which packets must be forwarded along the shortest path. So, that is what nbuv contains, that it contains that for the destination v, to which node should the node u forward a packet. Okay. So, packets with destination v must be forwarded to nbuv by u. Okay. Now, after this, we realize that there is a slight improvement that we can do to this, and that is that all those nodes for which duw is infinity, they will never update du, because duw plus, if this is infinity, if this term is infinity, then infinity plus anything cannot be lesser than any other finite quantity, right. So, therefore, those nodes for which duw is infinity need not receive the table dw. So, then the question arises, then which are the nodes which will receive the DW. Okay. Instead of broadcasting it, we can send it to a subset of the node. Okay. Now, to understand that how we can forward the table DW to only those nodes for which DUW is not infinity, let us first look at one lemma. So, the one that we are going to look at is as follows. S and W are given. Okay. What is S? S is a subset of vertices of V, and W is a node which is the current pivot. Okay. Then for all U, suppose DUW DSUW and if DSUW is less than infinity, not equal to W, then now this 1 and 2 are assumed. Okay. So, let S and W be given, and suppose that this holds and this holds. Okay. What does the first statement say? That for all U, DUW is equal to DSUW, and the second statement says that if DSUW is less than infinity and U is not equal to W, then NBUW is the first channel of a shortest S path to W. Okay. Now, if these are true, then now see, are each of these satisfied by the Floyd Warshall extension? They are, right, because this is the invariant which Floyd Warshall's algorithm maintains, that at any point of time DUW actually stores the shortest path distance from U to W through the vertices in S, right. That is what Floyd Warshall invariant maintains at each point of time, and it is preserved in the distributed version also. And if DSUW is less than infinity and U not equal to W, then NBUW is the first channel of a shortest S path to W. If this is less than infinity, then DUW is equal to DSUW. Okay. And remember that whenever we update this, we also update NBUW to point to the neighbor along which this DSUW is achieved, right. So, it always NBUW points to the next channel on the shortest S path to W. Okay. So, these two are guaranteed by the algorithm. Now, then what can we say? We say that then the directed graph then the directed graph TW equal to VW, these are the vertices of the graph, these are the edges of the graph. And what are the vertices? The vertices of this graph are those vertices for which duw is less than infinity. Okay. And what are the edges of the graph? And ux belongs to EW if and only if u not equal to w and okay. So, what does this say? This says that the edges of the graph are pairs are like ux, okay, where x is the neighbor of u, okay, through which packets to w are forwarded. Okay. Now, this is the graph. Okay. I will explain the graph in very shortly, but what our claim is that this directed graph is a tree rooted towards w. It is a tree rooted towards w. Okay. Now, let us first understand clearly what is this tree. Now, remember that in our network, so suppose this is the destination vertex w, all right. Now, some of these vertices have dw less than infinity, okay. The ones which have dw less than infinity, for how did they become less than infinity? There must be some iteration where we updated duw, right. So, when we updated duw, at that time we also updated nbuw, okay. So, for any vertex u, if duw is less than infinity, then there is also some x, and this x is basically nbuw. So, this is our nbuw, okay. Now, what this result is saying is that if you take these edges, the edges from the vertices to the next nodes on their shortest S path to w, then that is going to form a tree, okay. Now, try to understand why that is going to be a tree. First of all, every node has only one neighbor, because nbuw is a single number, right. Nbuw is some single value. So, no node can have more than one NBUW, alright, and every node which has DUW less than infinity will have such a neighbor. Okay. Only thing that we have to show is there cannot be a cycle, right. All we have shown is that for every node there is another node to which there is a link by virtue of NBUW, right. So, there is a next node on the path to W, right. So, how many edges are there? If there are n vertices in this, then there are n minus 1, because for W there is no edge coming out of W, right. So, there are n minus 1 edges, right. Now, only thing, so it is a graph having VW vertices and V minus 1 edges, VW minus 1 edges, right. Now, what else do we need to prove that it is a tree? Either we prove it is connected or we show that it does not have a cycle. Okay. Now, suppose there is a cycle, then let us say that there is a cycle in this graph then we can say that ds u0 w is weight of y. Because I traverse this cycle and then I am back in that same node, then I have ds u0 w. Okay. Now, the only way that this can happen is if this quantity is 0, right, but that cannot happen because all the edge costs are positive by your assumption, right, then this sum can never be 0. So, therefore, there can be no cycle, right. This is nothing surprising. You think of any shortest path, a shortest path cannot have a cycle unless there are negative cost edges and there is a loop of negative total negative weight, okay. Otherwise, in no shortest path can have a loop, right. So, by virtue of this, what have we shown? We have shown that what this distributed Floyd Warshall algorithm does is that at every point of time when the algorithm has computed the values of the distances to the other nodes, it has actually computed a sync tree rooted at W. For the destination W, if I just look at the vertices for which DUW is less than infinity, and if I look at the edges from every vertex u to NBUW, okay. So, from every node u to the node NBUW, okay. Now, if I look at only those u's such that DUW is less than infinity and I look at only those edges here, then this defines a tree, right. Now, if this defines a tree, then we can use this tree only to transfer dw, the table dw which has to be broadcast in the original algorithm. Dw has to be broadcast in the w pivot round. Instead of broadcasting it, we can use this tree to actually, so this is a tree which is rooted at w. So, we can use this tree to send the routing tables to from w to the other nodes. Now, the problem here is that a node u knows which is NBUW, right. So, it knows the child, but the child does not know which are the parents. So, if you look at this node x, then x does not know that for u it is the next node on the path to w. Do you get the problem? But which direction is dw going to be transferred? So, dw is stored here, w has to broadcast it to everyone. Now, w does not know the structure of this tree. So, w does not know the identity of x and y, right. So, what is it going to do? Okay. So, we need another round of message exchanges for identifying the edges of the tree. So, in other words, dw, the node w will actually exchange information with all its neighbors to find out which are those neighbors which are pointing to it, okay, and it will then forward dw to them, okay. So, how many messages are we going to need in the worst case? Order E, right, order of E, where E is the number of edges in the whole graph, in the whole network, not only in this tree. Why? Because W does not know which are its parents on the tree. So, W will actually have to send it not only to x and y, but to its other neighbors also. Suppose Z is another neighbor, so W will also have to ask Z that, look, are you one of my parents in this tree? Okay. Now, x and y will say, yes, we are parents, your parents, because we find that x is going to say, because I see that NB x w is w. So, I know that I am your parent. Then similarly, you will tell x that I am your parent, right. But because these nodes do not know which are its parents, it will have to communicate to all its neighbors, and only the parents will respond back saying that, yes, we are your parents, okay. So, effectively we are having to communicate this message along every edge of the original network.
Why can't initially only when we are adding this table we keep storing the number of children with that?
Now, children, you know, see, this node knows that to reach w the next node is x. So, it knows the children, but the child does not know which are its parents. You see, every node is storing, what is it storing? It is storing the next node on the path to w, but it does not know which are the other nodes for which it is the next node on the path to w. So, I know that to send a packet to w, I will have to send it to him, but I do not know which are the other nodes which are going to use me to route packets to w. That information is not there with me.
Must be all neighbors, all adjacent.
May not be, because there may be some nodes which are using some other, say for example, see this node may be a neighbor of this, but it is using this one because that is the shorter path. Through me it is going to take more, because maybe this edge has a very large cost. So, you see that every neighbor of me may not use me because I may not be on the shortest path from that neighbor to W. Are you getting my point? So, therefore, since I do not know this, so I will have to communicate to all my neighbors, tell all my neighbors that which one of you think of me as the next node on the path to W, and then some of them will say that yes, according to our routing tables you are the node through which we are going to route packets to W. Then I will forward DW to these nodes.
Only after this full computation will this message start going again, but only to our children. That means once your Floyd Warshall algorithm is finished, after that when we see that these are our routes on which we want to send our this route to W, then we will start sending messages to all of them.
No. When is this happening? In the Floyd Warshall algorithm, remember that in every iteration we stop and pick one node W. All processes must pick the same W. In the original algorithm, the node W broadcasts its routing table DW to all other nodes, right? Instead of doing that, what now the node W does is, it asks its neighbors, which one of you are my parent in this tree? The ones which respond by saying yes, we are, only they are sent DW. The routing table is sent to only them. They in turn ask their neighbors that which of you use me on the path to W, and then the DW is forwarded to only them. Are you getting my point? So, the message asking that are you my parent is sent along every edge, because every node will have to send that message to all its neighbors.
Broadcast to one with a time to hop, like one hop.
Not broadcast. Every node asks only its neighbors.
The neighbors.
Yes.
One hop, like just hop to neighbors.
Yeah. So, it starts when W is selected as the pivot. Okay. W asks all its neighbors. It asks all its neighbors, are you my parent? Are you my parent? Are you my parent? Are you my parent? Okay. And then out of these, let us say that two of them say yes, I am your parent. This one says yes, I am your parent. Then DW is sent to only these. DW is sent to this. DW is sent to this. Okay. Now, what do these two nodes do? They in turn look at their neighbors and ask them, are you my parent on the path to W? Are you my parent on path to W? Okay. So, they ask all their neighbors. Only their neighbors, mind you. Okay. Now, out of these, let us say that here all three of them say yes, I am a parent, yes, I am a parent, and maybe here only one of them says I am a parent. Then this node will send DW to only this one, this node will send DW to all of them, because whoever has said yes will receive DW. Now, see what is happening here. The DW is only going along the edges of the tree, but to find out which are the edges of the tree, we are sending messages along every edge of the graph. Is this clear? The way the thing is working, right? So, the number of messages that are being sent is order of E. And how many times is DW being sent? DW is being sent order of VW. Okay, this is the number of DW messages and this is the total number of messages for the pivot round W, right. Once the DW reaches all the nodes on the tree, then they continue with Floyd Warshall's algorithm, like updating once they get the DW here, then they use this updation, okay, and the Floyd Warshall algorithm continues, and again in the next iteration it picks another W, okay. Then from that W again the same thing happens, okay. Now that tree is a different tree. So the tree rooted at W1 is not the same as the tree rooted at W2, because the tree rooted at W1 talks about packets with destination W1 and how they are forwarded from each node. Packets with destination W2 will obviously have different routes, so they are going to form a different tree.
Are we really saving on much of because certain some nodes are getting 2 messages, some nodes are getting only 1 message.
Yeah, but remember that DW is a heavy thing, right? It contains the entire routing table. So we are saving in sending DW to only order n or order VW number of nodes, right? And in the worst case we are sending order E messages in total, but the other messages are simple messages, they do not have much weight, okay. So if you look at the number of bits that are transmitted, then that is where this one is saving, okay. So based on this we can write down the complexity of the algorithm as follows, that this algorithm, which is basically called so this is the improvement over the distributed extension of Floyd Warshall, and this algorithm exchanges order n messages per channel. It exchanges order okay. Is it clear? N is the number of vertices in the network. So in every pivot round order E messages are being exchanged, right. So if how many rounds am I going to have? Order n number of rounds, because in the Floyd Warshall algorithm that S set grows by 1 in every iteration, so I am going to have n iterations, right. So n iterations, and in each iteration we are sending order E number of messages, so order of any number of messages in total, alright. Now the main drawback of this approach is that this broadcasting or sending the routing packets along specific paths, etc., this is the main drawback of this algorithm. So naturally we look for algorithms which can do the same computation but using more of local information, okay. So, to understand how we can use local information, we first observe that what is the inequality that Floyd Warshall algorithm tries to exploit. So, it uses the triangle inequality. So, it tries to use the inequality that duv, the distance from u to v, is less than or equal to duw plus dwv, right. This is a standard triangle inequality, that the distance from u to v will be less than or equal to du, the distance from u to w plus the distance from w to v. Okay. Now, the question is which w do we select, right. So, there it basically, the w's that we select are the ones which are added to S, right. Now, there is another way of looking at it. We can also use the following alternative equation, where we say that duv equals to 0 if u equal to v, and is equal to minimum among the w's which are the neighbors of u minimum of what? The weight from uw plus dwv. This is otherwise. Now, what we are saying here is that this is another dynamic programming formulation of the term duv. Okay. What we are saying is that it is the minimum among these quantities over the w's which are the neighbors of u. What does that mean? It means that if I have u and v is not equal to u, then the path to v must go through one of the neighbors. Okay. So, I have neighbors w1, w2, w3, etc. Now, this is the weight of this is wu w1, okay, and similarly these two weights are there, and suppose I am given what is the distance from dw1 to v, I am given what is the distance from dw2 to v, and I am given the distance dw3 to v. Then the distance from u to v is the minimum of this plus this plus this weight, and this plus this weight, right. It has to be that. So, we can make use of this to compute the routing tables using local information only. So, what does that mean? That means that in order to compute my distance to v, I am going to ask my neighbors that what are your distances to v, and when my neighbors tell me that these are our distances to v, then I will simply compute this term and find out my distance to v. Okay, right. Now, how do we actually do that? Let us see the next algorithm. So, this is a very simple algorithm, but it achieves the same purpose. Let us see how it works. So, what we are doing here is this is for node u. What does node u have? Its data structure, it contains du v0, which is a array of weights, and nbu v0, which is a node. Okay. So, we will explain this shortly. What does node v0 do? So, this algorithm is actually going to do the following thing. It is initiated by the node v0, and when it terminates, every node will have the shortest path distances to v0, and they will have the neighbors, identity of the neighbors along the shortest path. Let me reiterate. What this algorithm does is, it is an algorithm which is initiated by a node v0. When the algorithm terminates, at that time every node will have the shortest distance to v0, and it will also have the neighbor along the shortest path to v0, right. How will the algorithm work? It will start from the node v0. Node v0 is going to tell its neighbors, node v0 will tell its neighbors that, look, my distance to v0 is 0, right. My distance to v0 is 0. What are the neighbors going to do? The neighbors will see what is the edge cost from them to v0. So, they will see that which one is the that they will just sum that with 0, and that is going to be their distances, right. And then each of those neighbors, when they revise their distance to v0, they will tell their neighbors that my distance to v0 is so much. So, let me give you an example. This is node v0, okay. So, it broadcasts to everyone. What does it broadcast? It broadcasts the message, my distance to v0 is 0. This is what it broadcasts to all its neighbors, What does a neighbor W do when it receives this message? It will compute its distance based on that. So, suppose let us say that this distance is 5, this weight is 5, this edge. Then what does the distance become from W to V0? 5, okay, right. Now, what is this going to do then? It is going to send out messages, my dist V0 5. This is what W is going to send to its neighbors. Can W send this my dist message again during the computation? It can. How? Let us look at another neighbor here, x. Let us say that this distance is 1, right, and let us say that W is one of the neighbors of x. Now, what message does x send? X sends the message, my dist V0 1. Now, remember that W has already sent my dist V0 5. Now, it gets a my dist V0 1 message, right. Now, let us say that this edge has a cost of 2. Now, what does W see? W sees that through x I have a better path. because x is saying that it can reach V0 in one step, and I can reach x in 2. So, I can reach V0 in 3 instead of the 5 that I previously saw, right. So, now W will again revise its cost, and it is going to send out what message now? After receiving this message, it will again send out, but this time it is going to send out mydist V0 3. Okay.
Sir, if there is a node which is not connected to V0, say x was not connected to V0 also. If x was not connected to V0, would it still tell that my distance to V0 is 0, or what would it tell?
No, if it is not a neighbor, then it will not get the message.
It won't share also.
No, it is not going to get the message, right. If it is not a neighbor, it will not get a message, but it may not be an immediate neighbor. Suppose there is a y which is not a neighbor of V0, but it is a neighbor of some z, z is a neighbor of some q, and q is a neighbor of V0. If that happens, then mydist V0 is going to come here, then q will compute its distance to V0 and send that to z, z will compute its distance to V0 and then send that to y, and so on. Okay. And whenever there is an update, the NB pointer also changes. So, initially when W got this mydist V00 message, at that time the NB W V0 pointer at that point was pointing to V0 when it first got this message, but then when it is revised the cost by getting the message from x, what should this become? This will become x, right. So, at every point of time the node maintains not only the shortest distance to V0, but also the neighbor along the shortest path to V0. Is that clear? So, now let me show the code of this algorithm. So, it starts with node V0, where node V0 sets d V0 to 0 because its distance to V0 is 0, and for all W belonging to neighbor V0, it sends mydist V00 to W. So, it broadcasts to all its neighbors that its distance to V0 is 0. Now, what does a node U do when it receives a mydist V0D message from neighbor W? So, a node U receives from its neighbor W a mydist V0D message. What does this mean? The neighbor is telling you that, look, I can reach V0 in D. My shortest path to V0 is D. Okay. Now, what does this node U do? It receives the mydist V0D message from W, okay, and then it checks if D plus the edge weight from U to W is less than its current estimate of the distance to V0, then what does it mean? It means that we have found a better path. We have found a better path which goes through W. We have got a better path from U to V0 which goes through W. So, then what are we going to do? We will update the distance. Now, du V0 will become this better one because this is better. So, we update du V0 to this. Not only that, we also update NBU V0 to point to W, because now the best path to V0 goes through W. Okay. And now that my distance has changed, it is quite likely that my neighbor's distance will also change, because I have found a better path. Now those who were using me to route packets to W to V0 may also get a better path through me, because my cost has gone down, so their cost will also go down. So therefore you will have to broadcast this mydist message to its neighbors. So for all x belonging to neighbor u, send mydist V0 du V0 to x. How is it different from? It is not different from Dijkstra's algorithm, except that in Dijkstra's algorithm you synchronize and choose which is the node which can be frozen at this iteration, right. You choose one node which can go from open to closed, right. That prevents the other nodes being updated before they are due, right. Now look at what happened here. This W node, it got the mydist V00 message, and it has, because it is distributed, it had already propagated this mydist V05 message to its neighbors before the shortest path was discovered, right. So in the distributed sense, what happens is it is all happening in parallel. So all the nodes, because they do not know about the other nodes, they are all thinking that whatever I have got now is the best, and it propagates that. It does not wait until the shortest path to V0 from itself is discovered and then tell its neighbors. That is what happens in Dijkstra, because it is happening in only one process. Here, because of the distributed nature, a lot many more messages are going around. Okay. Is that clear? Now is this algorithm more or less understood, right? This is your first introduction to what is called a wave algorithm. This is called a wave algorithm. Why? Because it is starting at one node and it is propagating out to all the other nodes by virtue of communication between nodes and their neighbors, right. Now this is going to continue until the shortest path distances are arrived at. Once the shortest path distances are arrived at, then there will be no further reduction in the cost, and whenever there is no further reduction in the cost, the node is not going to transmit anything. So the only time when the node transmits something is when it is updating its du values, right. Now what is the number of messages that we are exchanging here? Can you give me an estimate? Yeah, so what is that figure going to be? Well, we can say that Chandi-Mishra algorithm exchanges order n square e messages in total. Now this is not for one V0, this is assuming that every node starts this algorithm. See, the algorithm that I showed you is one which is initiated by V0. Now every node will start this, because we need all pairs shortest paths, right, not only for packets with destination V0, but with destination V1, V2, V3, etc. So every node will start this, but the messages of these are not going to get mixed up, because you see that in all the messages we have my dist V0. For the computation initiated by V0, all the messages in that wave will be stamped with V0. Similarly, for all the messages started by the wave from from V1, we will have my dist V1, right. So, there are n versions of these, there are n different waves that are starting up, and in each wave we are having a worst case of n times e messages. So, that is why we get order of n square e. Okay. Try to digest this and figure out for yourself that in each wave we are going to have n times c number of messages, and therefore, in total for n waves we are going to have n square e messages. Okay. And if you have doubts, get in touch with me.